Hi everybody, today we're going to discuss logarithmic functions further, but now actually look at the transformation of logarithmic functions. Before we do that, we have a couple of pieces that go with our warm-up. The first is this Frayer model, which is actually meant to kind of help us reflect on some of what we already know. So if you notice, the one side has exponential function on it, the other has logarithmic. I'm actually only going to help you get started, and then on your own, I'm going to ask that you go back and look through your notes and see what else you can fill out. So let's start on the exponential function side. In the upper left corner, it asks us for the equation. So we will recall, and we can look in our notes, that the general form for the exponential function is f of x equals a times b to the x minus h plus k. And there are several things that we know about variables here. For example, I know that if this has a positive a, that it means the graph will be above the asymptote. If I see a negative a value, I know that the graph will be below the asymptote, and that's where we get back to growth like and decay like. And then to determine growth or decay, I know that that's connected to b. I recall that if b is greater than 1, it's growth, and that if b is between 0 and 1, it's decay. Some of the characteristics that we had looked at the beginning when we looked at this function included that y equals k gets us our horizontal asymptote, and h and k also dealt with shifts. So what does h tell me and what does k tell me? I'm hoping you recall that h deals with our horizontal shift and k deals with our vertical shift. And I'm going to pause there on the Frayer model. So for examples, we can definitely look in our notes. Be interested to see what we have for non-examples. Think about that. And then on the other side, you can go into your notes and see what you have for your logarithmic function notes, the equation, characteristics, examples, and some non-examples. And treat this as a living document, so to speak. So we can continue to add to this. In class, you can compare the neighbor and see if there are characteristics or anything that they have you don't have, and you can add to it. I would also recommend that you make it stand out in your notes. So for example, you could take your highlighter and highlight the key pieces on the Frayer model. Remember, the more colorful your notes, the more likely you are to use them. And maybe you use one color on one side and another color on the other side. Very nice. Let's now move into the warm-up for today. It says 5-5 Day 2 Transformation Warm-Up at the top. And let's read the directions together. It says, in the table below, generalize the effects of the transformations on f of x and its inverse function. -1 there is telling us that we are dealing with the inverse function. So we've done transformations before. This is not new. This idea of transformations is not new. So do you recall, even think back to like absolute value functions, for example, quadratic functions. When I had a parameter or a value here, plus or minus a number on the inside, what type of shift did that cause? So let me just give you an example. Like let's say, and I'm going to literally label this old. What if I had f of x equals 2 times x plus 8 squared? When I saw that this positive 8 was here, I knew that that was actually x minus -8, and then that was a shift left. That shifted the vertex of this quadratic to the left. So let's generalize here and say left by a factor of c. So like whatever that number was, I remembered I had a built-in negative, and it caused a shift left, c. If I had seen x minus 8, I knew that that was a shift right. Let's say I had a number out here like plus 10. Sorry for that noise, just let the bell pass. If I had plus 10 on the outside here, I knew that that was what type of shift? I'm hoping we're all thinking shift up, and I would say you are right. That is a vertical shift, a shift up by whatever that value was. It would shift, in this case we're dealing with a quadratic, it shifted the vertex up 10. And if that had been a minus 10, it would have shifted the vertex down by a factor of c. So these apply to all of our function families. We dealt with this with absolute value, quadratics. This would apply across the board, including our exponential and logarithmic unit. So I'm going to erase, you can keep the old, I'll leave the old, why not? But just remember, this worksheet is not meant for quadratics. I'm just making a connection to our prior knowledge. Now it's time to make a connection to inverses. So I want to make a quick note here at the top, or off to the right. Recall, inverses switch x and y values. And that's going to help me realize what the transformation is when I deal with the inverse. So for example, let's say I was saying left left 5. That would mean x shifted left 5. But now if I'm considering the inverse, that's switching x and y. So if I'm talking my inverse, I would have to say y is shifted, but does y move left and right? No. Our only option is up and down. So left is in a negative direction. Transferring this to inverse, which would be y, that would mean shifted down. So if my original function f of x had a shift left, dealing with x being shifted left, 5, as soon as I'm discussing the inverse now, I switch x and y, so now I'm talking about y. Y does not move left and right, it moves up and down. So left 5 would correspond to down 5 when discussing the inverse. So in general, down C. Let's keep going with our little green notes. If the green notes help you visualize it, please add them. Otherwise, follow the conversation and be with me for the conclusion. So let's say right. I'm going to pick right 3. So x shifted right 3. Well, dealing with an inverse, we're now talking y. So y is shifted. Again, I can't go, if I'm talking about y, I can't go right. Right, though, the direction headed right is heading in a positive direction. So that would be y is shifted up 3. So in general, if we were to generalize this, that would be a shift up by a factor of c. Let's now discuss if we have a vertical shift with the original function here. So let's say up 2, why not? So now we're saying that y has been shifted up 2. Apologies for the bell. Y has been shifted up 2. Once again, when we're talking inverse, x and y switch. So now we would be talking x. So now how do I connect this? Because x can't move up, but up is a positive direction. So if we're now discussing if we're now discussing x, up would correspond to going right. So x is shifted right 2. In general, we will state right C. Last but not least, let's say my original was shifted down 10. So y has been shifted down 10. Again, inverses switch x and y, so now I'm discussing x, but x can't move down, right? X is limited to left and right. Well, down is headed in the negative direction. So if I'm now discussing x, negative would mean going left. 10. In general, to summarize that conclusion, for my inverse, that would be left by a factor of c. This little piece here is called extra credit homework. It says, consider the function y equals f of x and the transformed function g of x. So pay attention to the names, right? Because here's f and here's g. Those are two different functions. It says, write an equation for g prime, or inverse. So this is the inverse, also called g prime, in terms of f prime. So the inverse of f. So this was inverse of g, and this is inverse of f, or f prime. The directions say, consider the function y equals f of x and the transformed function g of x. So notice I have an original f of x and then a transformed g of x function given for each of these. It says, write an equation for g, the inverse of g, in terms of the inverse of f. So I'm just going to show you how to do A, and then I would like you to try B and C and D on your own. So looking at what we're given, let's just first take stock of what we have. I am starting off with y equals f of x, and it says g of x equals f of x minus 1 inside parentheses. So that means that we have a shift of what? Well, inside I know that's a shift left or right. Is it left or is it right? Recalling that x minus h, negatives built in, so this would be a shift right 1. Looking at my chart, I know that if I start with a shift right, when I'm discussing the inverse, that corresponds to a shift up for the inverse. So writing g, the inverse of g in terms of the inverse of x, that means I take the inverse function of f and I would add 1, because this is now a shift up by a factor of 1. So the chart above will help you know and decide where you're starting, and then what is the corresponding inverse relationship of that transformation. So in summary here, we had a shift right 1. In terms of the inverse, that connects to a shift up 1. And I'm excited to see what we have for B, C, and D tomorrow. Let's now move over to our piece of graph paper. And at the top, we're going to label it 5.5 log transformations. 5.5 log transformations. And the first directions we're going to have are to graph f of x equals log base 2 of x plus 3 plus 1. Notice I'm very careful to indicate using parentheses what is part of the argument and what is not. So right away I know something about the location of this asymptote. So my question to you is, where is the asymptote? If you need to press pause to go look at your previous notes on how to find that out, please do so. But from my notes, I know that for log functions, the asymptote comes from h. So right away, I know that h is -3, which means my asymptote will be at x equals -3. So I bring this up because as soon as we were given a function, it's good to kind of think, what do I know about this function? We have that prior knowledge, we want to keep it in mind. Let's get our XY chart set up. This we'll put on the back burner. And we've been exploring which kinds of graphs we can, or excuse me, which graphs we do need a calculator for and which ones we do not. Using our inverse skills, we do not need a calculator to create this table. So as a group, let's right now discuss why that is. As soon as I see I have log base 2, it's in my best interest to figure out how can I get powers of 2 inside, because I know log base 2 of 2 will cancel and leaves me the exponent behind. So off to the side, let's make a note. It would be really nice to start off with log base 2 of 2. So how do I get to have that on the inside? I've got x plus 3. What value of x would cause me to have a 2 on the inside? Well, I know that log base 2 of a -1 plus 3 would get me that 2. So I will choose to have -1 as my first entry in the table. Without a calculator, let's now evaluate and figure out what that is. So I'm going to have log base 2 of -1 plus 3 equals, plus 1, can't forget that, equals log base 2 of 2 plus 1, which is super nice for me because I know that this is 2 to the first. Log base 2 of 2 cancels, leaving behind the 1, plus 1 equals 2. So that was working towards having 2 to the first. Now let's work towards log base 2 of 2 squared. What is 2 squared? Well, 2 squared is 4. So I've got x plus 3. What value of x would help me have a 4 on the inside? I'm hoping we're all saying 1, and I would agree, so let's keep track of that idea. 1 plus 3 would get me that 4, which is why the number 1 will be the next value in my table. Once again, let's not use our calculator. It's going to be log base 2 of 1 plus 3 plus 1. that's log base 2 of 4. But I'm going to choose to write 4 as 2 squared plus 1. Log base 2 of 2 cancels, leaving behind the exponent 2 plus 1 is 3. We technically only need 3 ordered pairs to graph, so we never want to lose track of that really nice property that says when I take log base 2 of 1, something really nice happens. So if I've got x plus 3 on the inside, what value of x would let me get a 1 here? I'm hoping we're all thinking -2, and I would agree. And if you're not sure, you can always write it down. Like I can say, maybe it's -2. Let me check. -2 plus 3, that equals 1. Hey, I'm in good shape. So to get that 1 to happen, I have to plug in a -2. So -2 will be my third entry in the table. Let's do the work. Log base 2 of -2 plus 3 plus 1. That gets me log base 2 of 1 plus 1. What is log base 2 of 1? From our properties, we know log of 1, no matter the base, always results in a 0. Plus 1 equals 1. I now have my 3 ordered pairs, which is awesome. And I'm going to ask that we now sketch a 10 by 10 graph, an accurate 10 by 10. So for me, I'm going to kind of keep mine to the right a little bit. So what's kind of nice is, let's say I want to just sketch out a little bit. So if this is going to be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So that's 10. And then I want this to be 10 right here. So 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So right there I know is going to be my origin. So I'll make a little dot, and then I'll get my handy dandy ruler so I can make a nice straight line. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then same across. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So take a second, let's get our graph going. Alright, we have our 10 by 10. Let's now graph our points. My first ordered pair is -1, 2. So I go to -1, 2, 1, 3, and then -2, 1. But you know, I don't know. I mean, how far is this supposed to go? Like, does it go all the way over here, over here? What's missing from our graph? And I'm hoping we are all saying the asymptote, and I would agree. From the way beginning, we discussed how as soon as I see this function, because I see x plus 3, I know my asymptote will be at -3. So if you have your highlighter, remember it's kind of nice if you put your asymptote with a highlighter dotted line. So 1, 2, 3. And as soon as my asymptote is on the graph, I have a much easier time of actually being able to see where this function is. Let's work towards having a nice curve here. So here's my original function, f of x, and let's actually label it f of x. Now, I'm just going to zoom out a little bit. This we've done. Now let's see how we're going to apply transformations to this. So the directions now say graph g of x equals negative f of x minus 4 minus 2. I kind of put that a little close. Let me move it down. Negative f of x minus 4 minus 2. We are now into the transformation part of this example. Let's kind of get a menu of what happens here. First, let's discuss that negative out front. Thinking back to our prior knowledge, is that a reflection over the x-axis or the y-axis? That is a reflection over the x-axis. Alright, moving on to the minus 4 on the inside. We know that that is a shift right 4. And last but not least, that minus 2 on the outside, that's a vertical shift down. So as soon as we see we're dealing with a transformation, get this list. This list helps your brain kind of put a framework on what's about to happen to our original graph. Now to graph this, there's a little bit of strategy to it, right? So first, we're going to sketch the flipped point first, and I'll show you what I mean by that. Then can do this at the same time. So let's come back up here and look at this graph. See if I can just zoom out a little bit. Perfect. Okay. Now let's first talk about this shift right 4. It means that this entire graph is getting shifted right by a factor of 4. Don't actually put that on your paper. I'm just being a little dramatic to make my point. So it means that this asymptote also shifted right 4. So let's move the asymptote first. So I know I said this first, but let's take care of the asymptote first. So shifting the asymptote right 4, that would go 1, 2, 3, 4. So that means my new asymptote is now at where? X equals 1. I'm going to see if I can change the color of this. If you have a different color highlighter, that would be cool. Hey, check that out. No, I don't want to use green. How about red? Purple? Nope. Blue? No, I don't like that either. Okay, look at orange. So my new asymptote has now been shifted right 4. Now we're going to get into dealing with the points. Don't want to lose track of this one, though. All right. So sketch the flipped point first, and then we're going to take care of right 4 and down 2. So what do we mean by flipped? Well, this was a reflection over the x-axis. So I'm going to change over to green. I'll use red. So what I mean is this ordered pair right now has to get reflected first. So if I reflect it over the x-axis, it's going to be right here. So what we're doing is we're taking care of the reflection first. Reflecting this over, this is 2 away from the x-axis, so it's going to be 2 away right here. And then last but not least, this guy, 1, 2, 3 away, so I count down, 1, 2, 3. So we just took care of the reflection. The reflection is done. And we have sketched the flipped points first. Let's just say points. Now we are going to shift right 4 and down 2. So watch. I'm starting right here. I'm going to go right 1, 2, 3, 4, and then down 1, 2. I'm going to do my new points in black. So we successfully shifted that ordered pair right 4 and down 2. Now let's do this one. Shift right 1, 2, 3, 4, down 1, 2. Took care of that one. One more to go. Taking this ordered pair, what are we going to do? We're going to go right 1, 2, 3, 4, down 1, 2. That was our last ordered pair to shift right 4 and down 2. Our graph is complete. And we can label this g of x. So looking at our original blue graph, this blue graph has been reflected over the x-axis, shifted right 4 and down 2. And what's in black is the result. Transformation complete. Let's now write the function for g of x. We graphed it, but what is its function? Let's consider what we started with first. So our starting function was f of x equals log base 2 of x plus 3 plus 1. This is what we started with. This was the given. We applied the transformations to this graph. Now we are going to apply the transformations to the function. Let's first apply the reflection. So I'm going to keep this line going a little bit to just keep track. If we have a reflection, that negative is going to be on the outside of the function. So it's going to be negative log base 2 of x plus 3 plus 1 and close parentheses. Parentheses are huge. So I'm actually going to highlight this right here, and I recommend you do the same. Because before we go any farther, we're going to take care of this first. What I mean by that is notice how we have these parentheses. So let's actually send in our negative to apply that reflection. So it's going to be applied here and to that positive 1 term. This becomes negative log base 2 of x plus 3 minus 1. Now we can take care of a shift right 4 and a shift down 2 at the same time. So negative log base 2. Shifting right 4 occurs inside the argument. So that's going to be plus 3 plus 4. Shifting right 4 is a positive 4. Let's highlight our transformation. The minus 1 is still here on the outside. And then shifting down 2 means minus 2. That will be on the outside. Completing our final function here, let's combine like terms. Positive 3, oops, I made a mistake. So shifting right 4 is not a positive 4. Remember, and I needed to remember in that moment when I was writing, to the right is minus. That whole idea of a built-in negative still applies. If I had shifted left, then I would have put a plus 4. My apologies. So, combining the terms, x plus 3 minus 4, we get x minus 1, and then on the outside, minus 3. And we have successfully found g of x. So before we wrap up this example, let's just put a couple notes. If there's a reflection, do that first. And remember to use parentheses. And then let's add a note so you don't make the mistake I did. Recall shift right is x minus c because of that built-in negative. Very nice. That concludes our graphing transformation example. Great job. And I look forward to any questions you might have on this. As always, any questions on this graphing example, please take a quick screenshot and shoot me a question on Remind.